So this is going to be a short summary of a very cool project that we did with my father, Georgy Karev. We actually did it a while ago, but I wanted to revisit it because I just think it's such a cool story. And it's about decoupling internal and external time in the dying brain and how you would actually model that. Okay, so the motivation for this actually started with a story by Ambrose Bierce and occurs on Owl Creek Bridge from 1890. And this is a story about a man who is about to be executed, and he escapes, he returns home, he is reunited with his wife, and then we find out that all of this actually happened in his mind during the moment of execution. Another maybe more familiar version of the story is this wonderful episode from Star Trek Next Gen, The Inner Light. And if you haven't seen it, it's lovely, highly recommend it. Picard goes into comes in contact with some alien artifact, goes into a coma. The crew tries to wake him up, nothing works. Only 25 minutes pass as they try to wake him up and fail. And for him internally, it feels like he has lived an entire lifetime while he was in this coma. And the common theme here is, of course, that perceived time is, in both cases, much longer than actual time. I mean, in one case, it's right before death. The other case, it is a coma. But still, kind of the same idea of decoupling of external and internal time. And, well, we were wondering, how would that work? So I started looking into some established models of time perception. And the main ones that I found, at least at the time, were the scalar expectancy theory. And the main idea here is that time is not a direct measurement of events, but it's more of a mental estimate, kind of based on interplay of a bunch of internal processes, attention, memory. If you pay attention, you actually make a memory, these kinds of things. And it also assumes the existence of an internal clock, which can generate and regulate these so-called pulses. And the more pulses you collect, the longer the perceived duration of an event or an experience. There's this SBF model. And the main idea here is that maybe different parts of the brain produce rhythmic signals, like little internal metronomes. And they're monitored in the basal ganglia. And when several of these rhythms align at the same time, then the brain marks the passage of time. So interestingly, dopamine seems to be able to regulate is involved in regulating how accurately and quickly this timing system works. I'm going to briefly touch on that in the end, but that was just an interesting thing. And then, so what we wanted to talk about really here is this idea of near-death experiences and time distortion. Yes, we could be talking about happier things, but, well, we're Russian. You do not want to know what cartoons I watched growing up. Okay, so how might this work? What might be happening in the brain? Well, during cardiac arrest or trauma or something really bad happening, I mean, obviously, you would expect oxygen supply to the brain to drop sharply. And again, you expect the neurons to start shutting down. But what if it happens not all at once? Which, of course, makes a lot of sense, that it would not all shut down at the same moment. And maybe in this window, the brain may enter a hyperactive state before total collapse, which is when this experience could be. So there were a couple of interesting papers that actually seem to indicate that maybe this is something that is actually happening. So this one was a 2013 paper published in PNAS, and the authors they designed an experiment where rats had heart attack, so they underwent cardiac arrest, and then the brain activity actually increased briefly, but to levels higher than during waking consciousness. This is a figure from that paper, especially the gamma waves. So the red one is the cardiac arrest piece here, and you can see a lot of them, these are much higher than during waking or obviously anesthesia. So that was really interesting. And then maybe you remember, maybe you don't, in 2022, there was this paper that came out where a man actually died while he was getting an EEG. And it seems to be the first full EEG recording from a human during death, because it was kind of this accidental experiment. And as you can see, we seem to be seeing actually kind of similar patterns, that after cardiac arrest, the brain activity doesn't go down. It actually is still high. So in this particular, like there are some obviously differences compared to the rat experiment, somewhat different. So this is the rat experiment that I just showed. Different waves, so gamma versus alpha, things like that. But it does seem like this is not rat-specific situation, that it does seem to be happening in humans as well. So that was kind of interesting. And well, then the question is, because we're modelers, how would we describe something like this? So the approach was to describe this is, what if we look at the brain as a population of dying neurons? And it is a heterogeneous population. So each subgroup, or clone is the term that has been used, dies at its own rate. So how would we formalize this? So assume you have this population, L of T, comma A. So L is would be the name of the variable subpopulation, depends on time, and also A would be the death rate parameter that is individual to each subgroup. And it's a big assumption, but still, assume that each subgroup dies proportionally to its frequency in the population. So you would have this subgroup L of TA divided by N of T. N of T is the entire population, so an integral if it's a continuous system, obviously a sum if it's discrete. K is just some parameter. A is the individual death rate of each subgroup. This is called the frequency-dependent model. And that means just that subgroups die proportionally to their frequency in the population. And that is important. Like, this whole theory holds or works if we assume that in a world where this is true, this is how neurons would die, then what would be the implications? Well, so what? Yes, assume that this is what happens. Well, the interesting thing is, and this is a theorem that was initially derived and proven by Georgy Karev, is that if the initial distribution of subgroups in the total population falls within a gamma distribution, which means that, so if you look at all the subpopulations and you say, okay, so this many subgroups have this value of parameter A, so this subgroup of neurons dies at a rate of, 1, and this subgroup dies at a rate of 5, and this one of 10, and if you put their frequencies in a graph, you will get this kind of a distribution. It's a type of a gamma distribution. Well, then you can actually rewrite the equation for total population size as power law, where you just have two parameters. So K is just a parameter, and P is the power that would have to be less than 1. Obviously, if this is 1, it's just exponential decay. So P, when P is less than 1, then it's sub-exponential decay. Okay, now this is now the actually really cool shtick here. Let us introduce a new variable that we will call internal time, Q of t, and assume that it follows this equation. So Q of t, the rate of change of Q of t, is UK divided by N of t. And it was chosen for a particular reason for this, but read the paper if you want to know all the reasons. But assume that the internal time, the rate of change of the internal time, is described by this equation. So you can very easily see that if N of t is decreasing, and it will be because this is a negative term, so it will just be decaying over here. As it increases, the Q of t, so your internal time, grows. So as total population size of your dying neurons is going to 0, your internal time is actually going to infinity. And if you accept this interpretation of this subjective or internal time, then one can say that it increases as the brain deteriorates. And it kind of is interesting because it's almost like internal time diverges from external chronological time, as this is something that's happening. That is very cool. So what would that actually look like? In a world where this is the model that would describe this process, well, assume that time to brain death is 10 minutes. So about 600 seconds can be estimated between 5 and 20 minutes, just taking a nice round number for illustration. Okay, so let's look at this. So on the x-axis here, I have the external time, so my 600 seconds. And on the y-axis is the population size of my neurons. So you can also interpret them as maybe connections between neurons, or quality of connection between neurons. We're just doing physical neurons as an interpretation here, but it's a model. You can find other interpretations. And we took it about 10 to the 11th as kind of an estimate. Okay, and you see, so this is in log scale because otherwise you can't really see much, that how much, so okay, over time, so as time goes to 600 seconds, your population of neurons goes down and down and down. It's like 10 to the minus 60th or something, so it's basically 0. Another way to plot this, or I was curious to look at it, so if you plot external time versus internal time, so my Q of t, again, as external time goes to, or chronological time goes to about 600 seconds, you can see, oh, your internal time keeps growing and growing and growing. And by the time here, it's like 10 to the 80th. It's enormously large relative to your objective, quote unquote, objective time. Or another way to visualize this, again, there are not too many variables here, so it's easy to do. You have internal time versus population decay. So kind of similar to this guy, but on the x-axis, instead of external time, we have the internal time. And you can also see, yes, as your population of neurons goes down and decays, your internal time gets larger and larger. So in a world where this is what happens, maybe this will allow you to live 40 years of a happy life on a dying planet in 25 minutes that it takes for you to wake up from a coma. So to summarize, this was proposing a framework for thinking about time perception by decoupling external and internal time. And it was formalized as this mathematical model, very simple model of sub-exponential decay, the power law model. As I said, it allows decoupling this internal and external chronological time. It can capture, in a world where this is true, kind of a range of scenarios. I mean, obviously, as we were talking about near-death experiences, so this perception of time, of life flashing before your eyes, and this is necessary, or this will happen if the different neurons die at different rates, then this framework would apply. But maybe subjective time perception as well, during trauma, psychedelics, neurological disorders, like dopamine, as I mentioned, is involved in time perception and deteriorates in a number of diseases, like in Parkinson's, for example. Well, what if your dopamine-producing neurons are affected or deteriorate at different rates? Not as dramatic as the death experience, obviously, but stretched out, maybe this is something that can be affecting the time perception. And maybe or more temporary things like time blindness that people with ADHD have, for example, or I think schizophrenia, or some disorders where this can be happening, or some psychedelics that could be affecting the dopamine receptors. So that could be interesting. And it was just really fun to think about and work on yet another project with my dad. So this work was actually initially done 10 years ago in 2015. And the framework, this was one of our first collaborations we did with my dad. I looked it up, it actually was the third one, but it's one of kind of my first very memorable one. The theory that the mathematical background here is completely developed by him, and the question formulation was by him, and then I went into the deep dive about the biology and experiments and time perception models. So this was the original publication, which does not reveal how cool this information is in here. Mathematical modeling of extinction of inhomogeneous populations. And recently I pulled out the more biology-centric preprint that I put up on arXiv, basically summarizing exactly what I just showed here. And if you really want to look at more the theory for describing of evolution of heterogeneous populations, the mathematical basis of this work, we put together a book with theory and a lot of examples in 2019. So please feel free to check it out. Thank you.